Is it really that time, or did somebody mess with a clock? No, it really is that time. So we're going to do our third equation, and I'll just say the name so that you can start practicing saying it in your head, and then we'll do it. Is the Bernoulli equation. Bernoulli. All right, let's just say what it is, and then we'll get excited for the derivation. What we're saying here is that the fluid conserves energy. So what have we done? We've done static. The continuity equation really was the conservation of mass, if it's incompressible. And now we're just going to apply conservation of energy and get a whole new equation that you can use in various cases. Let's do it in a minute. I don't want to do it right now. So 5 minutes. Doing the break early so I can warm up. Okay, so now we got to ask the question, how are we going to apply conservation of energy to a fluid? So to quote Khal Drogo, these are questions for wise men with skinny arms. Right? So 1 out of 2. I got 1 out of 2. Okay. So what we got to do is think back. How does conservation work? See, I was watching it, and like when you first jump onto it with the Philo, it shows you the quotes, and then you can actually read what he said. I don't actually speak the language. So we know this. If you have an isolated system, like a little bit of fluid, that's equal to delta K plus delta U. So here's good review for the exam, right? If you do external work and it's positive, and when is it positive? It's positive when you push along the displacement. You must be increasing energy. Right? If you do external work on something, you increase its energy. So one of these has to go, or the sum of these has to go up. You could have a case where you actually have kinetic decrease, like if you were to push it up a hill, but it slows down, but your potential is going to increase. Or you could have a case where potential actually decreases, but kinetic increases enough to make up for it. But the point is, together they must increase. If this is positive. I'm just giving you little word examples to think about. You could have negative external energy. That's where you catch something, or external work, where you catch something to slow it down. But the basic idea is if you do work on something, that'll go up. So all we got to do is apply that to some fluid system. So let's do work external first. Let's calculate that. And our little imaginary fluid system is going to look something like this. It's like a tube with some small area down there, but not so small you can't see what I'm doing. Here we go. A tube with some smaller area down here that goes up to a bigger area up here. And it also changes its height, such as to consider gravitational potential. We're just doing gravitational potential. We're not going to have the fluid push on a spring. Ooh, that's a cool idea. Write that down. Fluid push on a spring. Excellent. Final exam question. Okay. Okay, so what we want to think about is not really a little piece of fluid here displaces a piece of fluid here. We want to think about this whole piece of fluid right here in the thing. There we go. We're going to conserve mechanical energy for that piece of fluid. Okay? And now we want to think about the external work on it. So how are we doing work on it? Who's working on it? Like, it's just sitting there, right? The external work comes from the two pressures. So we have pressure 1 over here, and we have pressure 2 over here. Okay? And we're talking about the fluid flowing generally this way. So it's going at V1 over here, and it's going at V2 over here. Okay? So fluid flows through a pipe, changes height, changes area. There's pressures. We don't know which one's higher yet. Don't worry about it. And let's see. And we also have, do I need the area? I don't need the areas yet. That's all we need. Okay, so let's calculate the pressure, or the work. Here we go. Let's see. Work external. Well, what is work in general? It's force times displacement. Okay? So we want to think about the work that this side does. It's that pressure times that area is that force. And the displacement we could just call delta x, delta x1. Right? So we basically want to come up with little 1 subscripts for everything happening on the left. Okay, so it's pressure 1. I think we're using lowercase p's in this book. Pressure 1 times the area of 1 times the delta x of 1. Okay? So all these properties over here. Has a cross-sectional area of 1. In a time delta t, we move it delta x of 1. Right? All these things are happening. Okay, let's see. Where's my phone? I've generated a question already. Yes. Are the heights equal on both sides? No, right? This one is higher. You probably meant the diameters. No, the diameters are not necessarily equal. So this is A2, and it's bigger. I just didn't exaggerate it enough. Okay, so that's the work. So this one, this pressure, this fluid does external work because it's pushing it in the direction it moved, right? Positive pushed along the direction it moved. Pushed along motion. Now, what about the other side? All right, so on the other side, which way is the force due to this pressure? It's this way. And it moves to the right. So that means it's negative. Right? So I'm going to put a negative sign, minus, and I'm going to say P2, A2. There's the force, delta x2. Right? This is negative F against motion. So I just put the negative sign in. If you want, we could do a dot product and blah, 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 blah. But we're trying to kind of just get the ideas out, not do all the formal math. Okay? Then we could say, well, area, so this area is from the force and this delta x is from work, but then they go together and you get that P1 V1 minus P2 V2 is the external work. All right? It's just PV minus PV. So we're going to stop there. So we have our external work term now. P1 V1 minus P2 V2. And it kind of makes sense. Here, if the fluid is going forward like this pressure is adding to the energy. This pressure is reducing the energy because it's pushing the other way. Okay? This is like when you push the ball along this table. This is like when you catch the ball and stop it as it goes along the table. Okay? All right. So that is this term. Okay, we'll put that in a minute. Now we got to do the potential energy. Potential energy, the delta U, right? Okay, delta U. Here's a review for the exam. What is delta U equal to? Final minus initial. U final minus U initial. And if we're just talking about gravity, are we assuming the A's are equal? No, I just drew it horribly. I apologize. This one is bigger than this one. It's too late to redraw it. I can't. If I was on my computer, I'd just go, but I can't do that on here. I could tilt the, no, I couldn't do that. Okay, so U final universal. So these are gravitational potentials. They're just MGHs. Okay? They're just MGHs. So it's really just MG Y. Let's see. Well, what is MG Y1 minus M. I'm sorry. The final is it's going to the right. So it's MGY2 minus MGY1, right? Whatever the mass is, whatever the G is. So we're talking about rho. So the mass is rho times V times G times Y2 minus rho times V times G times Y1. All right? So that's the delta U, is how much some of the fluid gets lifted. It's really just how much, whatever volume we're tracking, it goes from here up to here. And it's the total rho, the total volume. Or the total volume to get the total mass. Yeah. Is V volume? Yes. So rho times volume is density. Mass, density times volume is mass. Sorry. It's mass, yeah. Okay, well that was it for potential. There's nothing else to write for potential. So we're done with that one. All right, and now let's do kinetic. We know that it's flowing. The velocities might be different, V1 and V2. We don't know if they're the same or different. We're not assuming anything. So we'll do kinetic now. Right, and we'll find that delta K is also final minus initial. So we'll get that delta K is 1/2 mv squared, where this is the final mv2 squared minus 1/2 mv1 squared. Right. How fast is some of it going? And then we say, well, those are, again, just rho v. Right? 1/2 rho v v2 squared minus 1/2 rho v v1 squared. How fast is it going when it's at the bottom and it's at the top? That's how much energy it gains. Right? Every little molecule goes through that and sees those different. So the reason I'm not doing subscripts on the volumes is because every molecule does this. Right? Every molecule goes from Y1 to Y2. Every molecule speeds up from V1 to V2. Oh, I gave it away. Or maybe it slows down. I forgot. I don't remember. Okay. So now we put it all together. We have all three terms, delta K. Oh my God, do we really want to write it? Let's see, all together. I'm going to save us a little bit of writing because this will just become a ridiculous mess. But we're going to say this equals that plus that. So what's going to cancel? Oh, shoot, nothing cancels. Oh, yeah, no, I remember now, yeah. So here we got to say, as we go back, so I changed notation in the middle of the thing. Is V1 equals V2 due to continuity equation? Okay. The same volume goes through. So you can actually write this as P1 V1 equals, or minus P2 V2. Minus P2 V2. That's what I meant to do. That's the other reason you can say all these V1s equals V2s is just V. So if you put it all together, all the V's cancel. That's the point. Okay. So I was going to write it without the V's at least. All together, the volumes cancel. So that's one of those derivations, as you're going along, every step doesn't make sense, but the end kind of looks like it makes sense, if that helps. Okay. So the V's are all going to cancel. It's very exciting. What's going to happen? What are we going to have here? Is we're going to have P1 minus P2. Right, that's the left side once you cancel out the V's. So somebody's asking, why is V1 equal V2, not A1 equals, when the A's aren't equal? It's the volume that's conserved regardless of what A does. Right? The velocities in the areas are different so that they're keeping the volumes equal. Because continuity says the volume is constant as you go through. So it makes up the big V with the little v's. Maybe you were thinking of velocity. So this, let's see. So now let's set equal to delta U, but let's get rid of the v's. This is rho g y2 minus rho g y1. Right? And let's bring in the v's, get rid of the v's, and it's 1/2 rho v2 squared minus 1/2 rho v1 squared. Right? So you look at that and say, we're not going anywhere. This is a nightmare. Right? Let's separate them by side. But let's put 1 on the left and 2 on the right. And then we'll see something kind of interesting. Right? We'll say, okay, the pressure of 1 plus its rho g y1, its potential energy, plus its 1/2 rho v1 squared equals on the other side. Negative pressure comes over P2 plus rho GY2 plus 1/2 rho V2 squared. And you look at this equation and you say the left side, 1, is everything going on here, and the right side, 2, is everything going on here. It doesn't really care about the volume. The volume went away. It just cares about the pressure there, how high it is there, and how fast it's going there. That's all that matters. So it seems to me that there's this quantity that's constant. Okay? I could have put this other part right here, and we could have done it. Or I could have put it here, we could have done it. I could have put it here, and done it. And you get a car. Okay? No matter where I put it, we get the same result. So this quantity we're looking at here on both sides is constant. It's a constant for the flow. All right? So we're going to put it right here. Bernoulli. So I'll put flow, because this is actually a liquid that's moving, is we say we know that the pressure, right, plus rho, rho gy, how high it is, plus the kinetic energy equals a constant. Shoot. Is a constant. Right? Anywhere you go in the fluid, you can say that's a constant. So that's how you solve problems, just like how you solve hydrostatic problems. Remember, in hydrostatics, you draw this dotted line. And you say the pressure here equals the pressure here. Let me use this equation and say that's equal at both places. For flow, you say, here's two places in this continuous flow. This here equals this here. And they don't have to be the same height anywhere. That's why it's a more complicated, exciting equation. Right, we're going to do a few examples. Okay. So how to think about it. So remember how you did energy, how you're doing right now in kinematics. All right, this is kind of what I just said, but I'm going to say it again. Energy and kinematics, what do you find? You find the initial and final. Right? The ball is up here on the ramp. It has some potential energy, and it slides down the ramp, and that converts to kinetic energy. And regardless of the shape of the ramp, if you just think about initial and final, you can get the velocity at the bottom. That's the whole exam right there. But let's look at energy in fluids, how this works, which is Bernoulli. All right? So you would do it more like this. You'd say, I have this system where it's flowing in this weird way. Ooh, like that. Whoa, look at that. It's like a duck. Okay? So what you would do is ID 2 points. Instead of initial and final, is find 2 points. Say you care about it here, and you care about it here, and say here. What if you had 3 points? Find n points, whatever it takes to solve your problem. I think we'll just need 2 for everything you're going to do. And the deal is, this is the same everywhere. P plus rho GH, or Y, whatever you want to call it, how high it is, Y, plus 1/2 rho V squared is the same at all your points. So that's how you use this information. Okay? Now, the other thing is the book will talk about streamlines, and that really just means always stay in the middle. Right? So technically, if we started to say, I'm going to put this point down at the bottom of the tube here and the top of the tube here, clearly that would get screwed up because then the height is wrong. So streamline just means that one little bit of fluid, what's it going to do? It's going to stay in the middle. So just do all your problems in the middle of the tube and you'll be fine. Oops, stay in the middle. That's all a streamline is. So technically, I would want to put this one up here in the middle of the tube, not at the bottom. What does it say under energy kinematics? Initial and final. I'm just reminding you how you do those problems. Kinematics is initial and final. Fluids is find the points and apply that equation. But they're both conservation of energy. Okay. Okay, it's about to get weird. Okay. What was that term? Streamline. That's correct, streamline. I'm not making fun of people, I'm just answering questions. Yeah, streamline means the little line where one little bit of fluid would go, and it's the place you want to put your 1, 2s, and 3s. Just put it in the middle of the pipe. You can't go wrong. We're not going to get into what's happening at the edge of the pipe. We're just talking about the middle. Okay. Okay. Now, you would think that this equations look kind of nice, and everything is fine, right? We can go now, right? No.